This simulation uses voiceovers. Using the lab pad is an important way to get the most perfect. Then let's get started. I've just received a message from my research friend. Go talk to Kim by the table.
Hi there, good to meet you. I'm a research engineer here at the Polymer Research Lab. In one of the processes, we're using cyclohexene, which we make from cyclohexanol with phosphoric acid through an elimination reaction. We want to see if we can find something other than phosphoric acid because phosphor, as a limited resource, is becoming prohibitively expensive. Could you help us find out how?
Interesting. I hope you're up for this challenge. When you're ready to return to the main lab room, click the small plant on the table. So that you can help Kim, we need to bring you up to speed on the fundamentals of elimination reactions. Go to the functional groups poster. Explore the functional groups poster. Are you ready for some questions about organic chemistry? Great. Let's see what's the main functional group in cyclohexene? You can find the structure of cyclohexene in the Media tab, in the image showing the elimination reaction with phosphoric acid. That's right, cyclohexene has a carbon double bond, which makes it an alkene. Cyclohexanol belongs to the alcohols. In chemical reactions, what is a leaving group in the molecule of interest? Brilliant. In elimination reactions, it's very important to keep an eye out for these. Do you know what a carbocation is? You've got this. Alright, let's get you ready to work in the lab. You can always return to this poster later on if you're more curious about the functional groups. Locate the lockers and open one of them. Raise your lab pad for more information. Find a lab coat inside the lockers and pick up a pair of safety goggles. Alright, on workbench 1, I've set up a basic distillation unit, similar to the one in Kim's. Enter the main lab room. Go to workbench 1. Before interacting with the lab equipment, you should put on some gloves. Find a glove box and click on it to put on the gloves. Click the distillation setup. In this distillation setup, we've mixed cyclohexanol with a few. Check out the different parts of the distillation setup. Raise your lab pad when you're ready to continue. Have you checked out the different parts? Great. Then let's see if you can answer a few questions about the setup. Where does the elimination reaction occur? Exactly, this is the reaction vessel where we've added cyclohexanol and phosphoric acid. Where do you think the cyclohexene product will be located when the reaction is finished? You've got this. The cyclohexene ends up in the round bottom bottle on the right, as it... Let me show you a more general version of the elimination reaction. Often, there will... Which sentence would you say best describes a typical elimination reaction within organic chemistry? Exactly, well done. Two substituents are lost, one on each of two neighboring carbon atoms, and a double bond. Alright, now it's time for you to really dig into a real elimination. Go to the hollow table. Your first mission today will be to carry out an E1 elimination reaction. Worry not, I will assist you. The acid-catalyzed dehydration of cyclohexanol to cyclohexene that Kim is working on is a type of E1 elimination. Acid-catalyzed dehydration simply means the net loss of water from cyclohexanol. Pick up the leaving group marker, and place it on the part of the molecule that could work well as a lead. Nice, good job. Alkyl halides are commonly used in elimination reactions, because halides can be really good leaving groups. Quick question. What happens to the electrons in the bond between the leaving group and carbon, when the leaving group leaves? That's right. The electrons go with the leaving group, which in many cases means that it will carry a negative charge. Try and think of an example where this will not be the case. Now click the bond between the leaving group and the rest of the molecule to break it. Very cool. Since we moved some electrons, let's consider whether or not we need to add some charges to the molecules. Add the correct charges to the two relevant atoms, and click Done when you think you've got it. Exactly. You have now successfully eliminated bromide from the molecule and added the correct charges. This was the first step in the elimination reaction. As you can see, the main molecule is now a carbocation. The next step involves a base, which will extract a hydrogen atom. Let's get it on the hollow table and get rid of bromide. It's no longer of interest to us. Click on the base. Great. The carbocation we've created is not stable, and it really wants to react. Click the electron pair on the base to activate it. Now choose the correct part of the molecule the base will react with. Brilliant. Did you get that? Hydrogen was extracted by the base, thus eliminating it from the molecule. What happened to the electrons that formed the carbon-hydrogen bond though? Yep, you got it. The electrons moved to form the carbon-carbon double bond. The type of elimination we just went. Did you wonder why the double? Go to workbench 2. Here you see 5 containers with different alkyl halides. You can check out the containers. Are you ready to continue? All right. All of these 5 alkyl halides can undergo elimination reactions. Some of them are far better starting materials than others. Place the container with the least E1 reactive molecule on the right. Click on the lab pad for more information. Nicely done. Can you do it for the other 4 containers as well? Place the 5 containers so they are ordered by increasing E1 reactivity, with the highest reactivity placed on the left. Click on the lab pad for more information. Good work. So, what was determining the order of reactivity towards the E1 reaction pathway? Exactly. The trick with the... Since you're so good at this, I wonder if you can figure out how it works for E2 as well. What I can tell you about this reaction is that it does not go through a carbocation intermediate, but happens only in a single step. What do you think the order of reactivity would be for the 5 compounds for the E2 elimination reaction? Genius. When only looking at the substrate and leaving group, reactivity towards the E2 reaction is actually the exact same as for E1. Because you're doing so great, be aware that in little Alright, let's go to the wall screen in the center of the lab room. In elimination reactions, there is something called Zaitsev's rule that determines... Click on the main elimination product of the reaction. Good choice. Let's see if you can handle the next one as well. Click on the main elimination product right on. Again. Click on the main elimination product of the reaction. That was a more tricky one, but you chose wisely. Click on the main elimination product of the reaction. Brilliant. Looks like you... So exactly what pattern did you observe for the main elimination products? You can go back to the different rounds on the screen to check the result again. That's right. And that's what's called Zaitsev's rule. The reason is, put simply, that the more substituted product will be more stable. The underlying reasons for this are a bit more complicated and beyond what we will go into here. Great work. It seems that you have a pretty good grasp of the basics of elimination reactions. I'd like to show you the E2 reaction type now, how it differs from the E1, and why that's important. Go to the hollow table. Do you remember how the E2 reaction was different from E1 on a general level? Indeed it does. This can be a bit confusing, but it's because the number does not refer to how many steps there are, but how many reactants the rate-limiting step depends on. And for E2, that's both of the reactants. Zaitsev's rule also applies to E2 reactions, and the type of substrates. To get working with the E2 mechanism, let's get the molecule back to where we started. Click back on the hollow table to rewind the molecule to its original state. Excellent. As you know, this molecule could technically follow an E2 pathway as well as E1. But we can change it to make E2 more favorable. How would you change it to make it more likely to follow the E2 path? Right on. This will make formation of a click the part of the molecule we should change. This is not the bubble. Right on. We could also have changed one of the other side group. Alright, I will now enable the E2. Check out the E2 mechanism by clicking the play button. Cool, right? I will now ask you a few questions about this mechanism. Why is the double bond being formed between the two carbons in the middle of the carbon chain? That's right. In a real reaction, what is the configuration of the product around the double bond? Exactly. In an E2 reaction, a product with trans configuration will be far more dominant, due to the fact that the leaving group and the base removed hydrogen will tend to be anti-para. Alright, really well done. As you've hopefully noticed, the products of E2 reactions are very similar to those of E1. However, the dominant reaction pathway can highly impact the exact configuration of the main. I think you're ready to get a crack at Kim's. Why do you think they're seeing this reaction product when using hydrochloric acid with cyclohexanol? That's it. The chloride in hydrochloric acid can act as a nucleophile and substitute the hydroxide group in what's called a nucleophilic. Which of these acids might be the best as an alternative to phosphor? Exactly. The corresponding base species formed with sulfuric acid are too bulky to work well as nucleophiles. This will mean the elimination reaction is favored instead. Alright, let's head back. Click on the molecule and I'll take you back to Kim.
Genius. Of course, the side products are due to competition from a substitution reaction using sulfuric acid.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100%